Hello, hello, hello. That's weird. How's everybody doing? Welcome. Let's raise that a little bit. I guess we can drop it. That's fine. Ooh, move it over a bit. It's every other Thursday at 5 p.m. So it's time for the Ask an Astronomer hour, which is exciting. And I'm Kevin. I'm an astronomer, as I always introduce, at the University of Arizona. And starting at the beginning of the pandemic, or near the beginning of the pandemic, I realized that maybe people might want to learn in a video setting. It turns out that that's kind of how people are learning now over, at colleges all over the place. But hey, I thought I'd do one that's a little, there's no homework, there's no tests. It's just kind of some fun lectures, and I get to use Space Engine behind me and also some visuals and stuff to talk about astronomy stuff. And I have all those on YouTube. There, once this is done, you can go watch this again. If you're watching this on YouTube after the fact, hello. If you're watching this mostly because Super Mario Frustration, then hello, you and me. We're gonna start this thing up in space, so that's for you. If you have no idea what that is, that's good. I kind of been doing this just without really a lesson plan. When you mostly start with doing these things as actual lectures, like astronomy lectures, you try to make lessons plans so you don't just randomly do topics. And instead I've just been randomly doing topics that have been interesting to me. And so I started doing astronomy topics in general, but now I'm kind of circling back. And today I want to circle back because a couple weeks ago I did a really interesting one. I really liked a couple weeks ago where it was about how astronomers take astronomy images and turn them into pretty astronomy images. Today, as I was doing that one a couple weeks ago, I was realizing that I actually never really talked about telescopes at all. So today we're going to talk about telescopes. And I'm going to go through telescopes and light, and we're going to kind of do a pretty broad overview on telescopes. And hopefully what I hope this does is it inspires you maybe if you to go and look through a telescope or even buy a telescope, which is kind of the classic tool of an astronomer. So before we get into telescopes, let's talk about why we might want to use telescopes. And maybe you're thinking there's no, of course I know why, but just bear with me. I do have a kind of lesson plan for today, and so let's get into Space Engine. So here we have Space Engine again. This is the program that I use. Space Engine allows me to fly around in space, which is pretty incredible. So you can see we're here on the Earth. And let's imagine that we are not on the side of the Earth facing towards the sun, but we're on maybe the darker side of the Earth. So if I kind of rotate around over here, we can maybe land. So you can't really see much, but if we land, we can look up. So here's our stars at night. Our stars, and we've got a comet here. I'll turn on my guide for, here's C2020 F3 NEOWISE, but we're actually going to go, and I want to set the time to now instead of when it was. Whoops. All right. So let's actually go to a side of the Earth that is not, because this must be the Pacific Ocean. So let's zoom out really far out here. Let's find a side of the Earth that does not have, so right here, if we set this to now, we see that all of South America is in the, we'll just plop ourselves in the middle of the Atlantic Ocean here. Bonk. All right, so now if we look up, aha, all right, so this is now, here's Andromeda, and we look up at night. Imagine we're looking up at night, and that's the subject of another, well, hi, Lancer, welcome. Space Engine is not free. Space Engine costs money. If you want a free program, there's a program called Stellarium that allows you to look around, but you can't fly around in the same way. Space Engine is definitely, though, worth purchasing. It's an incredible piece of software, especially if you like flying around in space. But anyway, this is what you would imagine if you were in the middle of the Atlantic Ocean. It's perfectly dark, and you could look up at night, right? And the thing is that with your naked eye, you see quite a few things, right? You can see the Milky Way. And again, as I was saying, this is the subject of another entire series, which is about how to stargaze, like naked eye stargaze, using like using just constellations to walk from different patterns. And that's an entire other YouTube series that I do once a month, and you can go find that also on my YouTube page. But if you wanted to like look at these objects and understand them better, the problem is that, you know, they're pretty far away. And, you know, they are hard to see very well with your naked eye. Like with your naked eye, if we even drop the brightness here, you know, this is kind of like generally like from where I live, this is kind of what it looks like at night, right? Like it's hard to see here even just with YouTube. Maybe you've got glare on your screen, but you know, last night I was sitting out in a backyard and I could see this. This is the square of Pegasus, and I could see this. And if I looked a little bit away, I could start to see this thing here, which is important. But like this thing right here, as I pointed out, is Andromeda, the Andromeda galaxy. And it'd be great if we could see that, right? And what limits us in our ability to see that is our eyes. Don't get me wrong, eyes are pretty miraculous. It's amazing that we have eyes. And the way that eyes work is that light comes in from the universe or from a planet or whatever, and it's essentially a little lens. We'll talk about this in a second. Focuses it on a set of cells in the back of our eyes called our retina, and those cells can differentiate different types of light, which is pretty cool. But the problem is that our eyes are a certain size, and so from the light that comes in through our eyes, the little, you know, like focuses in, certain things are going to look a certain size. And it'd be really cool if you could say, like, take a chunk of the universe, take a chunk of the sky, and magnify it, make it larger, right? Because, like, you could imagine taking a camera and taking a picture, and, like, you could do what you do in, like, TV shows where you say, like, enhance, but that's going to just smear the small, blurry mess out to a larger size. It's not going to do what you want. What you really want is to take the fact that that object is giving off a lot of light, but you'd love to be able to essentially refocus it in a way such that it appears larger, like appears larger to your eye. And that's what a telescope does. But let's back up, all right? Let's back up. Like, what we want to start with is not the idea that, we want to actually take a step back. And the first step is, let's think about light. So what is light? Well, maybe you know what light is. Maybe you know it's an electromagnetic wave or whatever, electromagnetic radiation. But if you don't know, light is essentially the transmission of electromagnetic energy through the universe. It is a wave, and also a particle, we'll get there in a second, but a wave of electromagnetic energy going through the universe. If you have an electric field and it changes, a changing electric field creates a magnetic field. And if you have a changing magnetic field, it creates an electric field. And so that allows for, that thing allows to build each other. A changing electric field creates a changing magnetic field, which creates a changing electric field, which changes a changing magnetic field. And so you get this thing where what you're actually going to see is that light is a self-propagating wave of electromagnetic, radiation. So here's our internet image right here, where you can see, as you see, that you've got this changing electric field, which is in the blue, and as it changes, it creates a changing magnetic field, and they kind of propagate. And so light is a wave of electric and magnetic energy that are working together to create each other as it passes through the universe, right? And when you have a wave like that, there are two main properties. Property number one is that if the wave is taller, that's a more powerful, more intense light source. And if we have a wavelength, which is a shorter wavelength, meaning these waves go like this, right? They're much shorter. You imagine stretching this thing up here so that it squishes in more, or stretching, pulling it out, and then you have a longer electromagnetic wave. Those are kind of the primary ways that this propagates, because light all propagates and moves through the universe at the speed of light, which is set, right? It changes, it'll move through with water at a different speed, or move through glass at a different speed, but it always moves at essentially the maximum speed that you can move through a medium. Hello, Zeptunia. Welcome. Oh man, we got quite a group today. So the question is, how, like, what does that mean? Different wavelengths. What does that mean? Well, generally, you actually interact with this all the time. You don't realize it. Our eyes can see light of different wavelengths. We kind of talked about this last time. But here is a pretty important chart. I like this chart a lot. This is the chart of electromagnetic radiation, okay? And so mostly I want you to look, here, let's do what I did last week. I'm gonna put my hand right here. I want you to look, whoops, that's not what I wanted to do. Let's drag me. Look at this right here where you have the wavelength, right? This is essentially showing long wavelength all the way to short wavelength, okay? And below it, you can see the actual length of the wavelength. So in meters, right? A meter is, you know, you hold your arm out, that's about a meter, a little bit more than a meter, right? A little more than 3 feet. If you're British or you're from a sensible country that uses meters, you know what a meter is already. If you're from America, you know yards, and a meter is bigger than a yard. This is 10 to the 3, which is 1,000 meters in wavelength. And that means the distance from the peak to the peak, okay? And so you can see microwave is 10 to the minus 2, 10 to the minus, I think, what does it say, 8, 10 to the minus 6, 10 to the, 2, 10 to the minus, what is it? Infrared should be 10 to the minus 5, excuse me. You know, it's weird. I never do use meters when I describe this. This chart does. All the way down to 10 to the minus 12, right? Which is very, 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 very short, okay? Visible, which is the range we can see and is represented here by this little tiny rainbow, is a very tiny chunk of this. And they give it in frequency in terms of hertz, which hertz is like, a hertz is a wave every second is 1 hertz. And so if you have a higher frequency, that's more waves every second, and a lower frequency, that's like less waves every second, because, you know, frequency and wavelength are inverted from each other. Can light have the only electric field, magnetic field? So you can't have one or the other because they'll propagate and set itself up, right? So that's a really good question, Natalis, because so the electro, like you would not have light then. You could have a changing electric field, it'll set up a changing magnetic field, but when it's self-propagating like that, that's the electromagnetic wave. But there's not like electric wave or magnetic wave in the same way. You can also see they give the scale of the objects, you know, so a microwave is like a honeybee length, right? You know, but all of these are waves. If you look up this and see X-ray, this is electromagnetic radiation. This is ultraviolet electromagnetic radiation. Visible, what you can see with our eyes, electromagnetic radiation. Microwaves, electromagnetic radiation. Radio, electromagnetic radiation. You're saying, wait a minute, back up. Microwaves are electromagnetic radiation? Yes. What a microwave is, the thing that you put food into, is just a fancy flashlight. You put your food into a fancy flashlight, and that flashlight has waves that are of the wavelength given on this chart around there, but it's tuned specifically to hit water molecules in your food and cause them to go, oh gosh, oh. And if all the water in your food starts doing that, it makes the food hot. Because heat is essentially molecules and atoms moving faster. And so essentially, if you wiggle all the atoms, smack them so that they start wiggling a bunch, that's what it is. So in a microwave, it's just a fancy flashlight. My cell phone here is a fancy flashlight. It operates at a longer wavelength that, you know, in the radio and microwave, sub-millimeter essentially, and that essentially that light travels from a little flashlight that like creates the light in here. It's different than the flashlight like that is in actual flashlights, but it has a little thing that creates electromagnetic radiation, so you get those waves that travel out from here to cell phone towers, right? X-rays, that's another fancy flashlight. It's a fancy flashlight that uses energy that's incredibly short wavelength, which passes through your body, except it gets hit by your bones. So when you take a picture in the X-ray, your bones absorb the X-ray, and all the flesh and tissue, the X-rays pass through it to the detector, right? Yeah, Zeptunia, cooking your food with a flashlight. This is why the thing is why I'm not that worried about, like, people are like, oh gosh, microwaves, don't they, like, you know, they destroy the, you know. Microwaves are essentially just a fancy flashlight. But our eyes can only see essentially a tiny, tiny little bit of this region, which we call visible. Such a tiny little region. And the reason that they're like that is because that's where the sun gives off most of its light. The sun gives off most of its light at a temperature in the visible, which means that all the objects around us reflect that light in the visible, and our eyes evolved to see that. If the sun had more light in the X-ray, which would be weird, maybe we would have X-ray detecting eyes, but that would be very tough, right? The universe gives off most of its light in wavelengths like that are short, you know, around here and over, right? Like really not, like they don't give a huge amount of radio, but like essentially sub-millimeter microwave to visible. And then there's a little bit less of this and a lot less over here of the energetic stuff, right? When I say energetic, I mean the other thing is that bluer light, ultraviolet, X-ray, shorter wavelength is more energetic light. That light has more energy, right? And this is why we get worried about using X-rays or gamma rays, because the energetic light can actually interact in some cases with our cells and cause damage and stuff to our cells. I should also say, and this is something that like people bring up all the time, light is electromagnetic radiation. If you want to sound insufferable, you describe light as electromagnetic radiation. Metallis. The reason that other like if so when it comes to heating food, you certain light would like regular flashlight, that light would mostly just get absorbed or bounce off, and you could heat food with like a red lamp that was at a specific wattage that was very warm, and so the warmth of the light of the heat that is causing the light would actually then heat the food up. But the thing is that a microwave is very special in that it's hitting the light or hitting the atoms of molecules in water at a very specific energy where the molecules bounce around. If the energy were a little bit higher, a little bit lower, it wouldn't do the same thing to it, right? It's like, imagine if you had a whole pocket full of change and the molecules only wanted nickels. Well, if you threw dimes at it or if you pennies at it, it'd be like, but if you threw nickels at it, which is the microwave, that's what makes the the molecules dance. That's how microwaves work. But anyway, gosh, what was I saying? I was talking about energetic radiation, and I was talking about electromagnetic radiation. You might have also heard of radiation. And so when you hear of something like being radioactive, like a uranium, that's a slightly different thing. Radiation means like particles or waves coming off of something. It's a generic term. But like radiation in like uranium or something, or radiation left over from a nuclear bomb blast or a meltdown, these radiation, that is particle radiation. That's bad, and that also interacts with our skins in a bad way. But electromagnetic radiation just means light. And there is electromagnetic radiation that is dangerous, right? As I was saying, like really, really energetic electromagnetic radiation, ultraviolet from the sun causes cancer through sunburn, and through, very similarly, X-rays and gamma rays are cancer causing, because if enough of it hits you, it can interfere with our cells and cause mutations in our cells, which can lead potentially to things like cancer. But some of these longer ones, they don't actually interact with us, right? Like you can see that human beings are the size of certain radio waves and like we know that they don't interact with us because like your cell phone doesn't get blocked. Like if you had a flashlight and shown it against the wall would block the flashlight. But my cell phone, the little antenna in here, it's sending off energetic radiation that passes right through our bodies and the walls and stuff to go to the cell phone towers, right? And that's generally doesn't do as much. Like we worry about like, with our cell phone's gonna and we now have people who've had cell phones up to their heads for enough years to look at long-term baseline, and it turns out no, most of those waves just pass right through our bodies. They're not cooking our heads like microwaves are, right? So the question then is, here's all of our wavelengths. We generally can see in the optical or the visible wavelengths. Well, how do we capture the light from space? How does our eyes work? Well, first off, our eyes have cells in it that, there's rods and cones. Rods are cells that can kind of tell dim things and brightnesses of things. And then cones come in like three varieties that can detect slightly reddish light, slightly bluish light, slightly greenish light, but there's a big amount of overlap in those. And so those cones, kind of like we talked about last time, they can work together to tell our brain, this is what color is something is. What I mean by color is the light, as you can see, of different wavelengths, that carries with it in our eyes a different color. So all the light here, if it's blue or green or red, that means it's a different wavelength. And so if you have a cell that can capture things of different wavelengths, imagine if you had eyes that had like cells in it that could capture infrared light, then you would be able to have larger, so bees actually can capture ultraviolet light. And so they see the world differently because they have special cells that can capture a little bit of ultraviolet light. Our eyes are not sensitive to that. So radio waves are generally the catch-all term for the longest waves. If it gets longer than that, they're very, very low energy, and it's very hard to see them. We think that there are, but like generally, radio and lower is all. Anything lower than radio, we just call it radio. Anything higher than gamma ray, we call it gamma ray. We sometimes call it like megahertz or terahertz radiation to delineate exactly how many hertz on the frequency this is. But like generally, there's not a lower. We just say anything lower than radio, call it radio. But it's very, very unlikely because radio waves are very low energy. And so if you get lower energy than that, it's really hard to detect that. So there's likely lower radio energy sources or electromagnetic sources, but it's just hard to detect them. So the question is, how do we capture these? Well, our eye, as I said, captures light of very specific wavelengths, right? And how would we build an instrument that could help us do better at this, right? So here is, I have this thing that turns off all of my browser things after I haven't looked at it in a while. Here is this thing that was invented in the 1600s. So in the 1600s, this guy Hans Lippershey, who was a Dutch like lens maker, realized that lenses, which were used to focus light and to help with like glasses and sort of things, lenses could be used in a very specific way. A straight line. Well, a straight line would be energy less, I guess. If I were to draw an electromagnetic radiation as a perfectly straight line, it would have no energy because the amplitude, which is the distance from the top of the peak to the bottom of the peak, would be 0. So it'd be energy less, not just because it's super long, which would mean 0 energy, but also has 0 amplitude. So you're right. If you drew a wave that was not even wavy at all, no energy. Well, Zeptunia, I'm hoping you're learning something, or you're just remembering things from high school and being like, maybe this is better than high school. I don't know. Hans Lippershey in the 1600s, he realized that if he took a lens and another lens, so you may have played with, have you ever played with lenses? Here, let me go grab a Fresnel lens. All right, so here's an example of a lens. This is one of my favorite lenses of science. So this is a Fresnel lens. Let's see if it works like I want it to. And the Fresnel lens is just a normal lens. It's made in a very specific way. I have it from this book here. Gosh, can you see that? Does that look like my giant eye? I hope it looks like my giant eye. That's the hope there. Big ol' eye. I'm gonna have to look at it when I get back on my own tiny video here because I mostly want to see how that looks. But oh yeah, it works great. Oh, perfect. That's exactly what I want. So what this lens does is light that passes through it, instead of going straight, gets focused, right? And so this Fresnel lens allows you to do that, like pretty flat. This is kind of the lens that lighthouse keepers and stuff make, and allows you to magnify, because the light that would otherwise come through. So you see this comic here, and as I move it out, the comic is bigger, on this. It's a little warped because this is like a floppy lens. But you can read things, magnifying lenses. You can read things because the light that would come out gets focused so that now your eye can see things, smaller details. And what Hans Lippershey realized was that if you put another lens farther away from that, so that this is the magnifying lens, that generally was used. But if you put another lens, he could gather large amounts of light from space or from far away, and it would magnify that like a magnifying lens. But magnifying lenses have a very specific focal length where, they work really well. If you put a magnifying lens too far away, right, it just becomes a blurry mess, as you saw with my face here. It's pretty blurry. But with putting a second lens, you can actually do this thing where, watch, the light from space comes in, and so you get a lot of light. This is a big amount of light, that more than our eye, which has a tiny little hole, can see. That light gets focused, and then you get the second lens, this small lens here, and that small lens unfocuses the light and passes it to our eyes, which means you're taking a bunch of light and putting it into a smaller thing that our eye can now see, right? So imagine our eye has this little hole, and that little hole allows and permits only a very specific amount of light. But if you were to take more and compress it down so you could squish it in there, you'd be able to see things that were farther away in better detail, right? So you could imagine, kind of like when I was showing, if I turn off the internet here, kind of what I was showing here, you could imagine that what a telescope is doing is it's saying, first off, I can see more light, and second off, I'm able to take something that's far away and actually take all of this and focus it down so that it can fit into our eye, right? And so this was called the refracting telescope. Okay, this object is called a refracting telescope, and he was like, this is pretty cool, and he patented it. And there was some other people at the same time who also patented this. This was a thing that, we sometimes think that science is all the most brilliant people, and we would never have done if they weren't around. But a lot of people were doing these things at the same time, right? There were people for many years across the entire world who were using and grinding and polishing lenses and looking at their properties. And the cool thing about this was that when this was patented and word spread around, first off, it was really exciting for people for war, because imagine if you're a person who's like, I really wish I could see people attacking me from far away. Here's something that does that. A guy in Italy at the time, in the early 1600s, he discovered it, discover this thing and realize, oh my gosh, this is what I've been waiting for my entire life. This guy was named Galileo. And Galileo made his own. He saw the patent, he heard about it. He said, I can make lenses like this, and made his own. Exactly, Metallis. Science is a community effort. Now, this is exactly the type of community effort sort of thing. So Galileo makes his own. And let me show you a picture of Galileo's telescopes here. So here's Galileo's telescopes, and you can see, that they're essentially long and very, very small. Like, they're not the largest lenses. You can see down here, tubum opticum vides Galilei inventum et opus quo solis, essentially this is Latin for Galileo made these telescopes, right? And you can see there's two telescopes here. You look down here on this end, and this is the end pointing towards space, as you would expect. But these aren't super duper duper big, because he was limited by the lenses he could make. But he made these telescopes, and with it, he was able to do things that, no one had ever done. Because at the time, the best way of looking at space before telescopes was with your naked eye and with these crazy here. Let me look up. Let me show you Tycho Brahe Observatory in Uraniborg. This is Uraniborg, Tycho Brahe's crazy observatory, and you can see here that Tycho Brahe and his little tiny assistant person here, he is using this crazy curve. There's also this super sad weird dog there. Let's open this up in another page here. You can see it's weird sad dog here. But essentially, this big curve thing and this right here, you look through this right here with your head and with special optics and stuff down here. This person stands down here and waits to see when he can see through this stupid little hole in the wall the object out there, and then that tells him the angle, right, 90 degrees up to 0 degrees that it's at, and you can then write these things down. There's other instruments that you can see in the background, armillary spheres and stuff that allow you to do this, but you have to just use your naked eye to actually tell where these things are. And you could do pretty well if you've got a giant protractor on your wall, but Galileo was the first person who could go, I can do better. I can enhance my eye and see things that are far away. And so Galileo, he was the first person, and this is one of my favorite things in all of astronomy is this little diagram right here. This right here, this is a gross looking version of it. I want a better version. Here, let's do this. This little version right here. There we go. This is Galileo looking at Jupiter through a telescope. So here, let's do that. Let's do that ourselves before we go into Galileo's version. So I'm going to turn the internet off here. We're going to go to Jupiter in Space Engine. So let's search for Jupiter. Now, I know Jupiter should be visible in the south. In fact, this is it right there, I'm pretty sure. So if we center that, and we look through our telescope at it, like Galileo, we don't have to go that far to look at it. So notice, I'm going to turn you're starting to see that the thing, so we reset, looks like a dot from, and you can go out. If you're in the Northern Hemisphere, if you are living in a place above the equator right now, even if you're living near the equator, and it's clear tonight, go outside tonight and look towards the south, and you'll see Jupiter with your naked eye. It's incredibly bright. It's near the south. It's near another bright thing, which is Saturn. Go and do it. Just trust me. It'll be, you can take some time out, But he looked through a telescope, so here's us looking through our telescope, and he noticed this. Notice that as I zoom through, these things are spreading out. Let's zoom in more than he could do. And he was stunned, because he was noticing, it's really hard to see Jupiter right now because it's actually not that bright, but he was noticing that there were these other dots on either side of it. And if we make time go by, if we float out, let's actually, if we would make, gosh, can I make time go by without, if I center this, I think if I make time go by, it's going to do that. That's not what I want to do. What these dots are, he noticed that over time, these dots were moving around the object. And that was weird to him, right? And so here's his picture of that. You see the dots, the circle, which is Jupiter, and the dots moving on either side, and the date over here on the side. And what he discovered, Canada's totally fine, you know. And the way you find it is go out, figure out which way south is. The sun will have set to your right if you're looking south, and look for the brightest things in the sky after the sun has set. Super easy. So anyway, you see here, all these descriptions, you know, the date and when he did it, all this. What he discovered was that Jupiter wasn't just sitting there by itself. It had little things going around it. And he thought, these must be like the moon goes around us. These must be moons going around Jupiter, which is upsetting, you know, to the entire natural idea that everything went around the Earth, or that the Earth was perfect and nothing else had anything going around it and everything was just naked going around. Like, this is a big deal. And it's what led to a bunch of, you know, to him being forced to recant his beliefs eventually. But what he inadvertently discovered is what we now call the Galilean moons of Jupiter, which you can see here, all the Galilean moons. And in Space Engine, I can do you one better. We can actually, let's get at, yeah. Whoop. Here's Jupiter. And as I rotate around, whoa, no. I really want to rotate around so that it's, oh my gosh, stop doing this. Can I? Oh. There's Jupiter. Is it that I've got this on? Oh, so Jupiter is currently not actually showing anything on it, which is very strange to me. I do not know why Jupiter, whoa, why is this like this? Why Jupiter is showing any actual surface properties right now, but it looks like, it looks like for some reason, oh my gosh, I really don't like that. But anyway, doesn't even matter because I've got this on. Apparently Jupiter is really, really broken right now in Space Engine, but it has these planets around, or these moons around it that orbit around over time, and he was seeing them, which is pretty incredible. All with a telescope that, you know, was incredibly tiny compared with what we have, right? So if we go back to his telescope, you can see he was able to do that with these tiny telescopes, which is mostly the fact that he was super, super, super good at like being patient and having really clear nights and stuff. And also, this was something no one had ever done in the history of humanity, so he was very excited about it, right? Oh, cool. We got some South Canadians here. Well, you guys, it's even up farther. It's you know, pretty nice. I'm going to have to figure out why Jupiter is coming up like that with Space Engine after this stream. I should write that down. And the thing is that after that, we started building bigger and bigger refracting telescopes. So most, you might have seen telescopes like this if you go, like, you know, to buy telescopes. This is like your classic, like in movies, they make telescopes that like they have like a telescope, and like if it's a nerdy kid, they put the telescope in their window. You would never want to look through a telescope at space through your window. It's too bright in your house. Take it out in the backyard, you know, and look through a telescope like this. And by the way, you know, this is like a pretty good beginner telescope. It's not the best, as we'll talk about in a second, but it's a pretty good beginner telescope. Generally, they're pretty cheap. And the thing is that we start building telescopes like this, larger and larger. But the problem is that light is a little annoying, right? So here's the largest. You want to see the largest optical telescope in the world? This is the largest refracting telescope in the world right here. This is Yerkes Observatory, and you can see that over here is where you would look through it, and there's one giant lens over here, and then another giant lens, you know, down over here. And so you need this long tube to take the light and slowly focus it way, way, way down in order to look through it, right? So this is the biggest it is. It's 40 inches across, right? So a little over 2 feet, the lens. Pretty cool. Pretty cool. Way over 2 feet, 40 inches. It's almost 4 feet, over 3 feet, excuse me, right? The other moons are not bright enough. They're not big enough to reflect the light, and so it was really hard to see. He only saw a few moon and not 72 because many of them are very faint and it took a long time for us to detect them using way more fancy telescopes. He just saw the really, really big ones. And I wish that Space Engine weren't acting like this. I can show you like Jupiter moons here. If we look at the moons of Jupiter, you can see that like these are the size of Jupiter's, of Io, Europa, Ganymede, and Callisto. They're, you know, bigger than our own moon in many cases, and 3 of the cases, right? And so they're pretty big, right? You can see here that like Io, Ganymede, Europa, Callisto from this opposition, this picture here, that the big ones, then the others are not nearly as large, right? So here's a picture showing, yeah, here we go. Look right here. You can see Jupiter down here, and like Callisto, Europa, Ganymede, Io. There's some other ones. They're not as big. There's some, you know, but then there's a lot of little tiny ones, right? Oh, all right. Bye, Septunia. Thanks for coming. So there's a problem with this, which is, this problem is that, like, you know, so here's Yerkes Observatory, right? And this 1897 photo of the 40-inch, right? Like, and you can see like polishing the mirror. Like here's a person with one of the lenses, right? You can not you know, the big lens, right? There's a problem with making telescopes this big. First off, if you make a telescope that's refracting like this with the lenses, it has to be really long, and the lenses have to be really big and perfectly polished on both sides, and they get, you know, heavy. They have to be held on the edges, and that's hard. And if they get scratches, that, you know, like on either side. And then the bigger problem is this: lenses don't bend light of different colors equally. There's a thing called chromatic aberration, which means that blue light gets bent more than red light, which means that the light doesn't focus to the exact equal point. So in this diagram here, you know, you see that the light gets focused. If the blue light gets focused to different to the red light, that means when you look through this, you end up getting chromatic aberration, like images. And like chromatic aberration images, like images with chromatic aberration, like you can see here that like, notice that like things look a little blurry color-wise, right? Like this is a, you know, a YouTube video where someone has done like a fancy YouTube effect of the same thing. But like, it means that like your images look blurry, color blurry. Like this is a classic image right here. It's hard to see that because it's such a tiny thing, because it's, you know, Wikipedia. But like uncorrected, like your edges have like a halo of like red or blue on them, you know, because of just how and like people in video games like to do this. But like, yeah, look at the edges of that like, you know, so if I open this up, look at the edges over here. You can see the blue and the red. This is bad. If you want to take crystal perfect clear images of space, you wouldn't want. It's exactly true, because the blue light wavelength is shorter than the red one, and when they pass through glass, when they actually pass through this glass here, if I back up here, if they pass through the glass, the blue light is bent differently as it passes through the glass than the red light, and they have different wavelengths, and that's why they're refracted differently. Pretty cool. So in the 1650s, 1660s, another guy named Isaac Newton came up with this, which is, he said, if I want to focus light, I don't just have to use a lens, I can use a mirror. If I take a mirror and make it curve specifically, it will also focus the light. So light will come in from space, this mirror will act like the lens and reflect the light focused back onto, in this case, another little mirror that's just flat, which here's the focal point, and then you put your another lens right here, and that way you're not actually taking light through here, you're taking light off of here, and this does not suffer from chromatic aberration. These lenses do not, or these mirrors do not suffer from chromatic aberration. This lens may, but it's a small enough lens that the effect will be much smaller than if you have a large one. And with a mirror, you can support it on one side. You only have to polish one side. You know, and you can make mirrors really, really, really big, right? So this is the reflecting telescope, and it was the first reflecting telescope was made by Isaac Newton. It's a real tiny little guy, like a little thing this big. Hopefully you can see that. Hopefully, yeah, good. And like, here's your classic reflecting telescope. This is, if you're gonna buy a telescope for your backyard, this is what I would recommend. Buy some, you know, fancy reflecting telescope like this one, something where you can. You know, light will come in this right here. It'll go bounce off of the mirror that's on the back side here, bounce off of a secondary mirror, and go up into your eye. And you're saying, but doesn't this thing block? Doesn't it block the light, this secondary mirror here? And it turns out it blocks some of it, but not a lot of it, not all of it. Stuff can still get in from space, and so you're not, you know, it's not blocking the way. And so you can still see things when you look through this little eyepiece here, which has the actual second lens that actually is like the magnifying lens that's magnifying this giant image that you're taking out of space, put into a much smaller area, right? You've got all these other things here. These are weights and knobs, which allow it to rotate. I don't want to get into how it's mounted. Generally, you mount these things to follow the sky. You should watch my other YouTube series. We'll talk about that. But for right now, mostly remember that what a telescope is doing is it's taking a large amount of light from space, from a region of the sky, and shrinking it down to a smaller area so that our eye, or as we'll talk about in a second, a camera, can take an image of that. So it's spreading the light out, or taking light and focusing it down so that we can then take those images, or our retina can spread that same large amount of light out over and see more detail. And so the question then is, how big can you make mirrors? Well, here's a big mirror. This is a giant panorama image of one of the largest single mirrors in use. This is the Gemini 6-meter mirror. I've actually been here. This is in Mauna Kea, Hawaii. So we're up on the top of the sacred site for the native Hawaiian people here. And this telescope mirror is one giant polished, perfect mirror. Light comes in from space, bounces off this mirror, bounces off a secondary mirror up here, goes in through this tube right here to where, they collect the light, right? So the CA doesn't happen in the reflecting telescope, the chromatic aberration, because the lens is a concave. No, the chromatic aberration doesn't happen because it's a mirror, and mirrors don't have chromatic aberration. When blue light bounces off a mirror, it bounces the same angle as red light and the same angle as yellow light. And green light. All the same wavelengths bounce off a mirror. There's going to be some lenses, and there'll be a little bit of chromatic aberration, but it won't be nearly as bad as it is with large lenses like they would have to have if you wanted to make a lens this big. Right. Also, a lens this big is a lot of. Years ago, you went to Community College Observatory and saw it through a hydrogen alpha solar telescope. So what you probably saw was a telescope where they had a special filter, a hydrogen alpha filter, and I'll tell you about that in a second once we get to the second half of this. Mostly, I just want to talk about how these telescopes work just before we get to it, because like the next big thing is what you put on the end of a telescope and what sorts of things you put there. But essentially, light comes in, bounces off the primary, the secondary in, and comes to get collected in here. Now, with a telescope like this, you can put your dang eye right here. But you never want to put your eye on a telescope like this, because these are telescopes. This is a professional telescope, right? This is a professional telescope. And at the bottom here, underneath it, are all of the instruments and filters and things that will help take the light that's now been focused in through the telescope. It doesn't happen in mirrors because it's not passing through a medium. A mirror is reflecting the light. The light hits the mirror and bounces off the mirror. But with a lens, it goes through the lens. And when it goes into a different medium, red light behaves differently as it passes through glass than blue light does. They bend differently. And so that's when you go through a medium, light gets weird. When you bounce off a medium, you're good. It reflects it the same way. But I'm glad we're having some good questions now. So with a professional telescope, what you put on the bottom is not an eyepiece to look through with your eye. There's some telescopes that are pretty large that have eyepieces, but generally you don't. You put a camera. And so like special cameras that you stick on the bottom will essentially act like a DSLR or something like that. You can unscrew the main lens and you stick the camera on that, and that camera acts like your retina, but it can take pictures. Before we had digital cameras, which you could stick like on the bottom here, some of the first telescopes, the cameras you'd put on these like this would be cameras, like first of all, you'd be doing eyepieces, but you'd also take photographs. This right here is a photograph, an actual photograph. Like you'd take, just like with a regular camera, like a photo film camera, you'd stick that on there and you'd expose the light from space to the camera, like to the film. Then you'd close it, take it, go to a dark room and develop that film, and you'd get this picture of Messier 51, right? And we can actually go and look at Messier 51. Oh gosh, we are so bright. We can look at Messier 51 through our program here to see. Turn the internet off. Oh, window, yeah. To see, let's go there faster. So here's Messier 51. Boom, right? And you can see it. We can rotate around it as well. How it looks, but from the telescope, right? It looked a lot different. And in fact, from the telescope, if we bring up the telescope here, turn the internet back on, from the telescope. Hello, internet. All right. Nope. Just. Whoops. Oh, no, it's because I've done this, haven't I? Boom. That's why. There we go. From the telescope, you can see, I guess it's flipped upside down because that's how the thing's going to work. Let's do this. There we go. You can see that. Here, we can rotate ourselves, can't we? Sorry for the... There we go. Ba-ba. Aha. And you can see that, like, you know, pretty good for a giant refracting telescope. But with a bigger mirror, bigger lens, you'd be able to see more detail, right? Like Hubble can, the reason we have this image is because Hubble, which is in space, got a way better, more clear image of the same telescope, of the same, galaxy, and was able to understand more detail, right? Space Engine is very cool if you've not ever played with it. But this is from 1902, so pretty good for 1902. So what you'd want to do this and not just look through an eyepiece, because then you can have an image, like this image allows you to tell something that you couldn't do with your naked eye. You can also expose an image for longer than you could with a naked eye, which adds up the light more, right? So with a naked eye, through this, if we were to zoom back out, let's this is what I was going for. I was a little distracted. With a naked eye, maybe the galaxy would look something like this, right? Like kind of hard to see, a little dark, but with a telescope, with a camera on the bottom, you can actually open up the shutter for longer and add more light in, and slowly light gets added in, and you build up the light, and you get more and more bright. In fact, you could actually even saturate, as you're seeing here, but it can get brighter and brighter and brighter and brighter, and you can see more and more details on this thing. And that's the joy of having an actual camera on the bottom of your telescope, is that you can take photographs like this, or even cooler, you can take digital photographs, which allow you in a computer to tell how much light hits the pixel. And for that, you remember the last time we discussed, it actually is. It's two galaxies that are swirling around each other, Metalis. And you can go back to the Galaxies video from like a couple weeks, months ago, to learn a little bit more about that. But for right now, what's cool about having this picture and having digital pictures, like if we look at M51 Hubble, is that the Hubble image of M51 here tells us like a lot about the gas that's in the galaxy and the types of stars being born. All the things that I talked about in the Galaxies video from a couple months ago, like you learn because you can take a picture, because there's a camera at the bottom of the telescope, and you can put cameras on these telescopes as well, right? You'll get pretty good pictures, and there's entire Instagram accounts that are about doing that, right? The cameras that are on the bottom of telescopes like this, they're professional grade cameras. They're cameras that are designed specifically to do this, and they're cameras, they have a filter wheel in front of them. So this gets at the question, or the thing that Kevin Nguyen brought up earlier, which is he went to a community college telescope and looked through and saw like the sun, right? So the sun through hydrogen alpha filter looks like this. Here's your classic sun through H alpha filter. And what an H alpha filter is doing, so let's open this up. What an H alpha filter is doing is it's acting like really fancy sunglasses. So I've got my sunglasses here. I think I've done this before. I think we did this last week. It's got really fancy sunglasses. So here, let me turn this on. And the sunglasses make the light a little darker, right? So you can see me through here. Man, it's not doing a great job trying to do green screening at the same time as it's also looking through. But it's using sunglasses are taking the amount of light and reducing it. But an H alpha filter is saying, I'm only going to let light of a specific wavelength through at 656 nanometers. This very specific wavelength of light is where hydrogen glows, and so this allows you to take most of the light from the sun, which is way too bright, and reduce it down so that you can see it and see all the prominences and stuff. So the telescope was just a regular telescope, and if you took that H alpha filter out, you would like destroy your eye by taking the sun's light and focusing it. Never look at the sun through a telescope unless you have a very specific filter, right? And in this case, this would be an H alpha filter, right? You can look at the sun in like space engine or something, but like regular telescopes would just completely destroy your eye if you looked at it. Even looking at the moon through a telescope like this, I've looked at the moon through a telescope like this, and like it hurts your eye. It's like way too bright because you're taking a lot of light reflected from the sun off of the moon and putting it on your eye. Too bright. So one of the things about telescopes is that telescopes like can only work if light from space gets to the planet. So this diagram shows wavelength of light down here on the x-axis and how much the light can actually get through. So if it's 100%, no light gets through because it's completely opaque. That's what this atmosphere opacity is. But light in the light that we can see, red, orange, yellow, in the visible, generally it gets through. The opacity is pretty low here. Also, radio waves, they get right through the atmosphere. The atmosphere does not care about radio waves. Long wavelength radio waves are blocked from the atmosphere as well, but our atmosphere blocks most of infrared light. It has some windows here, but the oxygen and water, mostly the water in our atmosphere, they block the infrared light. And similarly, any really short wavelength light, X-ray, gamma ray, ultraviolet, our atmosphere blocks it. It doesn't do a perfect job. You get some ultraviolet, which is why we worry about sunburns and stuff. But thank goodness our atmosphere is blocking most of it. So the question is, man, it'd be really cool if you could see X-rays, but you can't put an X-ray telescope on our planet. The atmosphere blocks that light. Metalis, that genie was lying to you. Do not look at the sun if a genie recommends it. That is my Kevin recommendation. You could build a radio telescope on the Earth. You could put an optical telescope on the Earth, like the ones you look at through your eye. But an X-ray telescope, can't put it on the Earth and you wouldn't see any X-rays. An infrared telescope, pretty difficult. You have to have, in specific wavelengths, where these windows are, you could do it. And I've done that, right? From the Earth, I've used, where you go up to the tops of mountains where this whole thing is reduced by a bunch because there's less atmosphere to block the light. But what you really need is a telescope in space. And so that's what these diagrams here are showing. And telescopes in space, like this one, do a pretty good job of taking images at wavelengths you can't see. And because there's no atmosphere, the atmosphere tends to blur light. And so this is a cutaway of the Hubble Space Telescope, which is just a fancy version of this. Right? Like light comes in from space, it bounces off the primary mirror here. And you can see it says primary mirror, and it's pointing to this red and blue thing. It bounces off a secondary mirror here, and then goes into where the instruments are. That's it. It's got this aperture door that opens up, but it probably doesn't need to, close up very often anymore. Probably was open when it was, first was launched on a space shuttle. But that's literally it. It's just a fancy version of this, where instead of the eyepiece being on the side here, the eyepiece is on the back part. And so in this case, you're seeing that the light is passing through the mirror. The primary mirror has like a hole in it, and the light goes right back through it to where the instruments are, where all the cameras are. And because it's out of the atmosphere, it has a little bit of ability to see in the infrared. The telescope that I work on, the James Webb Space Telescope, will even do better because it's primarily an instrument where it will look at wavelengths between, 1 to 30 microns. This whole region will not have to worry at all about looking in specific windows. It'll get the whole thing, right? And there have been telescopes like Kepler and, not Kepler, like Spitzer and Herschel and some other telescopes that look at longer wavelengths, right? If you wanted to look at radio waves, you would need a bigger telescope. And so this is a telescope that's been in the news recently. This is the Arecibo radio telescope. What in their atmosphere is blocking the higher wavelength light? It is a bunch of molecules. It's hard to explain that. There's a lot of molecules that block higher wavelength light as well. It's just that X-rays can get interrupted and they get smacked into various molecules and particles, and that, and so if you could build telescopes on our planet that can see X-rays, but not the X-rays themselves, but when the X-ray hits a particle, that particle goes flying through the atmosphere and gives off a little light, and you could put a telescope that looks for that light, but that's not what I don't want to get into that right now. But essentially, this right here is a radio telescope, and a radio telescope does a similar thing to a reflecting telescope. The radio waves reflect off of this big surface to this, but there's no secondary mirror, and and this mostly just serves to sit here, especially this thing right here, to sit here and just capture whether or not it sees radio light. And so you have to have this because the radio waves are so long that a regular mirror the radios would just pass right through the mirror. With a large grid, like this, and surface, you could actually reflect radio light. And so you can use radio telescopes like this. This was in the news because something fell off and broke part of the telescope recently, which is kind of a bummer. It's in Puerto Rico. Here's an image from it. It's Also very famous because it was used. Yeah, here's another panoramic view of the main dish here. It was used. It was in the film Goldeneye. It was used as like the radio receiver that like was supposed to send the signal to the Goldeneye satellite, which you don't need a radio telescope this big to send a signal to a satellite, but whatever. If you wanted to look at really energetic light, like X-rays, here's the question. So I just said that you need a dish this big to capture radio light, right? Would you need a really, really tiny mirror to capture X-ray light? How would you capture light that is so energetic that it passes right through our skin, right? And it gets absorbed by our bones. Well, the way that you do that, the way that you build X-ray telescopes, and I'm almost done right here, is you have to be very clever. This is the Chandra X-ray telescope right here. Actually, where's Chandra? This is the Chandra X-ray telescope. It's really long. It's in space, and X-ray light comes in right into here and hits on the instruments right here. But notice it doesn't have like a big hole with a mirror. It has these like weird like circle with a triangle thing. What you're seeing here is this. You're seeing a set of mirrors that are actually not flat towards the X-rays. They're in like these onion layers. And they're nested paraboloids and nested hyperboloids. What they're doing is the X-ray light is coming in, and instead of bouncing directly off it, it's just subtly grazed. Kind of like if you had a bunch of bulls running and you wanted to capture them. You wouldn't want to just like stop them with a wall because they could break through the wall, right? If you slowly limited their space, they'll slowly focus. And so the X-ray light grazes just barely off of these mirrors here to reflect down onto your instrument here, which can tell you, like, so this is focusing the X-ray light onto a surface, allowing you to use a telescope like this to take images of the X-ray sky, which is pretty incredible, right? Oh no, chat's disconnected. Okay. And so here is an image of the same object in a bunch of different wavelengths, right? Where you can see that different telescopes, radio waves, kind of rough to tell the sorts of things going on there. Infrared, visible, ultraviolet, Chandra telling you X-ray stuff, and then even higher energy, you can see this high energy X-rays. You can learn this, and all of these types of telescopes work in concert on the same sorts of objects to tell us what's going on, what the processes are in things like this exploded supernova, right? So it's 5:57 right now, and I think I've gone through most everything I wanted to go through for this. I just threw a lot at you. In a couple weeks, I might go and do like another one where we just kind of do telescopes of the world and show some interesting videos and stuff, because it's interesting to learn about them. I'll talk about adaptive optics then, which is a pretty cool thing. But if there's any final questions, I really appreciate Metalis, especially Kevin, Zeptunia, the people who've been watching. It's been really nice that you guys have been asking questions throughout. That's great. And my recommendation is, if you want, binoculars are like 2 telescopes. They're pretty good for looking at things like the moon. Telescopes can be expensive. If you buy a telescope, it's good to buy one that has the ability to, maybe there's some GPS so that it can know where it's pointing, because it makes life a lot easier, especially if we can track objects over the sky. But otherwise, there are, in non-coronavirus times, there are star parties you can go to where you can look at, thank you, Kevin, where you can go and look at through people who own big telescopes and look at them. Community colleges, as was said earlier, they have telescopes. Planetaria sometimes also have observatories, and colleges have observatories. And go look through a telescope. It's pretty amazing, especially because, to go see what Galileo saw, to see Saturn and Jupiter. It's a bummer right now that many of these places are closed because of the pandemic, but when they're not, it's a good place. It's also a nice place to take people on dates. As a person who ran a planetarium for years, it was a pretty fun place to take people on dates. Well, Metalis, if you have space questions, as I do, follow me on Twitter and Instagram, and you can ask me in Twitter. Just tweet at me and say, hey, here's space questions. I love answering questions about space. No one asks me questions about space on Twitter. Do it. And join me in a couple weeks. We'll talk some more about this. I said 2 weeks ago that I would do a session where we go through and make astronomy images, but I realized that I wanted to talk about telescopes first. So maybe next time we get telescopes of the world, and then we go through and show, we finish up what we talked about a couple weeks ago and make an astronomy image from Hubble images. We turn it into a pretty astronomy image, which should be fun. You can definitely ask one last question here, Metalis. Go for it. You've had great questions. I really appreciate it. Meanwhile, let's go back to Earth. While we're waiting for the question. Earth. Welcome to Earth. While we go there. Turn this down a bunch. Gosh, Earth is so pretty. It's so ridiculously pretty. We're so lucky to have this planet, everybody. We're so lucky. Metalis is taking a while with their question. And remember tonight, Jupiter. It's pretty important. It should be something like, gosh, let's actually go and land. Australia. Let's land over in the East Coast. Let's land in southern Canada here. Man, is that Jupiter down there? Oh, it's Mercury. Okay, yeah. Yeah, looking south, you should be able to see it. It'll be a little low on the horizon, but you should definitely be able to see it. How do quantum fluctuations, the law of conservation work together? Well, that's a complicated question to ask at the very end of my thing, and especially because I don't exactly understand the question right now, so I don't know if I can help you right now. Quantum fluctuations, the law of conservation. Yeah, I don't know if I know enough. Small delay between us, man. Yeah. I don't know if I know the answer to that question quickly off the top of my head. Quantum fluctuations and the law of conservation. Law of conservation. Like conservation of energy? Because there's lots of different laws of conservation. Conservation of mass, conservation. And quantum fluctuations, it's not... I'm an astronomer, which mostly means I deal with space stuff, not quantum mechanics, which is more complicated. I'm sorry, I don't know if I can answer your question right now. I wish that I was a physicist and I could better answer your question. I gotta finish up because I'm getting pretty hungry and it's almost dinner time. And I'm sorry that I have to end on and not be able to answer your question right there. But you've had a bunch of great questions that I think I have answered, so I feel like on the whole, I did pretty well. Anyway, have a nice rest of your evening, everyone. Go look for Jupiter tonight and Saturn. They're right next door. You get a package deal. If you wait long enough, you can get to see Mars as well. Like if you wait till like midnight, you can come back out. And so if you watch eventually, so like right there's Mars. No, it's not. Where's Mars? Mars should be also visible. Oh yeah, right there. There's Mars. So in one part of the sky, you get Jupiter, Saturn, and you go all the way across, you can see Mars. Pretty cool, worth seeing. But have a nice rest of your evening, everybody. This was fun. I appreciate you guys coming out. Bye.